So the next question that we have is a series of questions as subparts. The pressure of the monoatomic gas increases linearly from 4 into 10 to the power 5 newtons per meter square to 8 into 10 to the power 5 newtons per meter square when its volume increases from 0.2 meters cube to 0.5 meter cube. We need to find out the work done by the gas, the change in internal energy of the gas, the heat supplied to the gas, and the molar heat capacity of the gas for the process. So for this, I prefer to first draw the graph. So, and it is favorable to draw the PV graph because the work done is asked. So when we draw the PV graph, we find that the pressure increases from 4 into 10 to the power 5 to 8 into 10 to the power 5, while the volume increases from 0.2 meter cube to 0.5 meter cubes. This is 4, this is 8 in 10 to the power 5 newtons per meter square. This is our final PV graph and it increases linearly, therefore this is the process that we are talking about. The gas goes from state A to state B while its volume increases from 4 to 8 10 to the power 5 newtons per meter square and its volume increases from 0.2 to 0.5 meter cubes. We need to find out the work done by the gas. So for finding out the work done by the gas, there is a very simple method. If you can draw the PV diagram. If you know the PV diagram, the work done by the gas comes out to be equal to the area under the curve, that is equal to this area in this case. So if we can find out this area, we can easily find out the work done by the gas. Therefore the work done by the gas will be equal to the area of this trapezium. Now area of the trapezium is equal to half into sum of parallel sides into the distance between them. The sum of the parallel sides is 12 into 10 to the power 5 newtons per meter square into the distance between them, that is 0.3 meter cubes. This comes out to be equal to 1.8 into 10 to the power 5 joules. So we get the answer for the first part very simply, that is 1.8 into 10 to the power 5 joules. Now we need to find out the change in internal energy of the gas. For this, we have a simple very direct formula. Delta U is also always equal to NCV delta T. Now CV is equal to F by 2 into R delta T. This becomes equal to, F is the number of degrees of freedom. For a monoatomic gas, F becomes equal to 3. So this becomes equal to 3 by 2 into NR delta T. Now NR delta T can be written as delta of PV, that is P final V final minus P initial. V initial is equal to NR T final minus T initial. On substituting the values of P final V final minus P initial V initial, this is equal to PB into VB, that is 8 into 0.5, that is 4, minus P initial into V initial, that is 4 into 0.2, that is equal to 0.8 into 10 raised by 5, which comes from here. Now on solving this we get delta U is equal to 4.8 into 10 raised by 5 joules. So we again get the answer for the second part, that is 4.8 into 10 raised by 5 joules. Now for the third part, we need to find out the heat supplied, which is pretty simple. Q is equal to delta U plus W. This is the work done by the gas. Work done by the gas is 1.8, delta U is 4.8. Therefore the answer for the heat supplied to the gas comes out to be equal to 6.6 into 10 raised by 5 joules. So we get the answer for the third part as 6.6 into 10 raised by 5 joules. Now we need to find out the molar heat capacity of the gas for this process. So for any process, we know that heat capacity can be written as Q is equal to NC process delta T. This is always true. Now we know the Q, that is 6.6 into 10 raised by 5. This is equal to C of process, that is the molar heat capacity of the gas for the process, into N delta T. We already had delta U is equal to NCV delta T. Therefore N delta T can be written as delta U upon CV, delta U upon 3R by 2. Therefore on feeding the value over here we get 6.6 into 10 raised by 5 is equal to C of process into 2 times delta U, that is 4.8 into 10 raised by 5 upon 3R. Therefore, the C process becomes equal to, this gets cancelled, 6.6 into 3R upon 4.8 into 2. This is 8, 11. This becomes equal to 33R upon 16. Now R can be written as 25 by 3. Therefore, 33 upon 16 into 25 by 3. That becomes equal to 275 upon 16. So our final answer for the molar heat capacity for the process comes out to be equal to 275 upon 16, and hence we get our answers for all the 4 parts.